In this video, we're going to talk about pressure, more specifically vapor pressure. These are your learning targets. We are focusing on two different diagrams today, the vapor pressure diagram and a phase diagram. Previously, we looked at this heating curve and we talked about when heat is added to a substance, temperature increases when it's a solid and a liquid and a gas. And on a heating curve, we also looked at these plateaus on the curve, and this is where the phase change happens for a substance, right? So down here, the phase change would be melting when heat is added. Up here, the phase change will be vaporization. And if we were to do the opposite, to take heat away, then this going the opposite direction would be condensation, and then this would be freezing. So remember, at these phase changes, when heat is being added, the temperature is constant because the heat is being used to overcome the intermolecular forces, right? And the stronger the intermolecular force and the more energy that's going to be needed to overcome these forces. And so we are focusing here. We're going to talk about boiling point today as we talk about vapor pressure. So I want you to imagine boiling up some water in a pot, and let's pretend that the lid is closed, okay? What's going to happen as the water starts to boil? If you said that the lid is going to start to rattle and maybe some of the water might spill out, you're absolutely right. So why is that? What is actually going on in the inside? So we know that when heat is being added, the liquid water is going to boil and turn into gas, right? So then why is it that the lid rattles, or why is it that even we might see some of the steam come out? It's because there's too much pressure that's built up inside, right? So let's talk about what's happening. Okay, so as we heat up the liquid, the molecules they have enough energy to overcome the intermolecular forces to go from being a liquid to a gas, right? So by doing this, there are molecules in the vapor phase that's above the liquid that produces a pressure, and that pressure is called vapor pressure. So vapor pressure, by definition, is the pressure exerted by the gas on the surface of the liquid. Okay, so this here is a vapor pressure graph of water. So this on the x is temperature, on the y we have vapor pressure. ATM stands for atmospheres, and standard atmospheric pressure is 1 atm. So standard atmospheric pressure is actually the pressure at sea level, and the normal boiling point of a liquid is measured at 1 standard atmospheric pressure. Now if we were to look at other pressure units, some units that you know about is PSI. Especially if you work with cars, right? So PSI is the pressure unit that we use for our tires. Some other pressure units that you'll see in chemistry is kPa, kilopascals, or torr. Now we have different pressure units depending on the type of equipment that we're using, okay? So liquid boils when the vapor pressure equals the atmospheric pressure. So if we're looking at standard atmospheric pressure, in this case it's ATM, so we're looking at 1 ATM, and so we take that across, and here it hits the vapor pressure graph. This, if you take it down, this is the boiling point, 100 degrees, and this is of water, so it's 100 degrees, which is the boiling point of water, okay? This is another example of different vapor pressure graphs. As you can see, they are different substances, and you'll see that they all have different vapor pressures at certain temperatures. They also have different boiling points at the standard atmospheric pressure, okay? So here's 1 atm. This is another pressure unit, millimeters of mercury. So standard pressure is also 760 millimeters of mercury. And again, you see that there are different boiling points, okay? So stronger the intermolecular force, the higher the boiling point, okay? So if you look here, the strongest one out of these substances is actually mercury, okay? The one with the stronger intermolecular force, the higher the boiling point, and the weakest intermolecular force, that tells us the lowest boiling point, is diethyl ether, okay? And again, we see different vapor pressures because these substances all have different intermolecular forces. So we're going to use this graph to answer a couple of example questions. The vapor pressure of water at 60 degrees. So if we take a look at this graph, and we're focusing on the water curve here, all right? So we're looking at 60 degrees, and we take that up to the graph, and we take it across as straight as you can, okay? That is about 150 torr. The vapor pressure of ethanol at 60 degrees, again, same temperature, except we're looking at ethanol, the graph above, or the curve above. Again, take it as straight as you can across, and that's about 350 torr. Now, I want you to focus, go back to this and focus at this part here. Stronger the intermolecular force, we talked about on the previous slide, stronger the intermolecular force is higher the boiling point, but I also want to talk about stronger the intermolecular force is also tells us that it is the lower vapor pressure at a given temperature, okay? So out of these two, the two that we just looked at, water and ethanol at 60 degrees, which one has the lower vapor pressure? It's water. So that tells us that water has the stronger intermolecular force out of those two substances. So from this graph, we can see that water has the strongest intermolecular force, and I'm not looking at this one here, so I'm just going to cross that out. So from this graph, we can see that water has the strongest intermolecular force, followed by ethanol, and then diethyl ether, right? Because by the time we get up to this graph, that curve will be all the way up here, okay? The normal boiling point of ethanol is, so for this one, again, the normal boiling point we're going to get when the standard atmospheric pressure hits the vapor pressure curve, okay? So for this one, we're focusing on ethanol. And the standard atmospheric pressure is given to you here, and this is of torr, all right? So we're looking at 760 torr. So that's the line that's given across here, okay? 760 torr for ethanol, so we want to go up on this graph, and it's where they hit right there, and that is telling us that it's 78.3 degrees Celsius. That is the normal boiling point. The next graph that we're going to look at is a phase diagram, and a phase diagram is a graph of pressure versus temperature that shows in which phase a substance exists under different conditions of temperature and pressure. So this is a blank phase diagram over here, and when we fill it in, we have the three states: solid, liquid, and gas. This is also known as a wine graph because it kind of looks like a wine glass here holding the liquid. I've also told my students that it's a butt graph. So it looks like a butt where it releases gas, just two different ways to remember this phase diagram. And where you see these black lines, this is where the two states coexist. We say that they're in equilibrium. So at this, like for example, this particular pressure and temperature right here, we have both solid and liquid, right? Which makes sense because if you're melting something, you have both solid ice and liquid water, right? Over here, like at this point or even this point here, depending on what pressure we're at, what temperature we're looking at, liquid and gas coexist. Liquid and gas are in equilibrium. So what do you think this line? What about this line? What two states will coexist? Solid and gas, right? Now, if we have a substance that starts as a solid and we were to increase the temperature, then we have a melting phase change. And if we were to do the opposite, lower the temperature, then our substance would freeze. If we have a liquid and we maybe increase the temperature or even lower the pressure, we get vaporization, and on the opposite, we get condensation. Now the two phase changes that we actually have not talked about is when a substance goes from solid directly to gas or a gas directly to solid. So a solid directly to gas is called sublimation, and a gas directly to solid is deposition. So what I mean is that when a solid goes to gas, it completely skips over the liquid state. So for example, like dry ice, right? Dry ice, we have solid ice, and when you take it out of its container, it just goes directly to gas. That's an example of sublimation. So I am showing you these different phase changes here. Go ahead and write that on your notes. And it shows you what state it's at and where it's going to. Okay. So if we were to look at this graph and look at a couple examples, if a substance is at this point right here, okay, what variable could I change in order for this substance to melt? All I would do is increase the temperature, right? And if I increase the temperature, then my substance simply melts, and now it is a liquid. And from here, what if I want it to vaporize? Well, there's two options, right? You can either increase the temperature and it'll go into the gas state, or you can decrease the pressure and it'll go down this way into the gas state. Now, if I had a substance that was a solid, so right here, what variable would I change, and how would I change it so that my substance would go through sublimation? All I would do, or all I have to do, is decrease the pressure, and then it'll go through sublimation, and now it'll be a gas substance. Now on your notes, there's also a section where it's talking about which phase changes are endothermic and which ones are exothermic. You guys have probably already written down that melting and vaporization are endothermic, right? A substance needs to absorb energy. It needs the heat in order to melt or in order to evaporate. Well, another one that you would write as endothermic is sublimation. And the other three are exothermic: freezing, condensation, and deposition. Those would release energy. Okay? Now at this point here, where all three come together, right here, this is called a triple point. And the triple point is the point on a phase diagram that represents the temperature and pressure at which all of the three phases, or all the three states of a substance, can coexist. So that's where we find solid, liquid, and gas. And that's it for phase diagrams and vapor pressure diagrams.